Okay, everybody. How are you doing? Hanging in there? Okay. So, I don't know if you'll be disappointed or not, but you don't have an in-class session today. Okay, so there's nothing due by midnight tonight. There'll be another assignment due on Tuesday, all right? But I was honestly behind on things, so that's where we are, okay? Any questions administratively before we get going? Yes.
In terms of the content that's covered on the exam, yeah, what content is going to be covered, or like what's the last? You know what I'm saying?
Sure. So the exam is on the 24th, right? So that's about 14 days, 2 weeks from now. Okay. So I anticipate that we will get through most of Torsion, okay, about a day before the exam. Okay, does that make sense? And then so if we go according to the syllabus, the class session right before the exam, we should be covering beam bending, okay, and that won't be on the exam. Okay, so essentially, we're going to be looking at axial loading, normal loading, and torsion as the main two topics. And if you look at the previous exams, the previous exam ones, that's what you'll see. It's usually heavy on axial loading and torsion. Okay, did that help answer the question?
Yeah.
All right, great. And on that note, in terms of how to study, all the equations that you would need will be in the notes. Okay. I think the only thing I can think of that wouldn't be in the notes is, okay, we need to know that rho times g times volume is going to be a force associated with weight, okay, of an object. And I think that's come up in the assignments. That's what comes off of the top of my head. Not that you'll have to use that, but that's like one equation that maybe I didn't explicitly put on the slides. Okay. But I also uploaded the past syllabi. Okay, so syllabus from 2022, syllabus from 2020, 2016, 2015. And if you want to look at Hibbler, that's fine. Please go for it. I feel the textbook's optional. If you look at the types of problems that end up on the exams, right, they are different though than the types of problems at the end of Hibbler's chapters, right? So it's still more similar, I think, to the types of problems that we're doing in class and on the assignments. Okay. Any other questions? Again, on the exam, one sheet, handwritten notes, both sides, and don't artificially zoom down your handwriting within reason, if you're doing it in a digital format, right? But no screenshots, no. And maybe we should, we're just going to keep it like that, all right? So it needs to be handwritten. Okay. Gives you a chance to process things. Okay, any other questions? Should we get going? All right. So today, the session was initially titled Torsion 1, but after the last meeting we had together, I thought that I should go back and review some things that were not clear, that I didn't do very well in class, and to provide more examples on axial loading. And I thought it was a good opportunity to insert an exercise on finite element analysis. So when we get there, we're going to do a little demo. If I can pull it off, we'll be happy, okay? And then on this assignment, that'll be one of the interesting foci that you get to do, okay? But we'll get there. So that's what we're doing today. And then we'll just, at the very end, we'll just start on torsion and kind of go through this mind-bending derivation on connecting the the angle of displacement, okay, to shear strain in a shaft. Okay. All right. So here we go. We're gonna get into axial loading. Actually, I think we'll do the thermal strain and stress before we do the finite element analysis, and then we'll get into torques and torsion on a shaft at the end. So this slide is pretty much what we had in our last session, slight with actually just maybe a little bit less material than I showed last time. So if we have a bar, okay, we're back to axial loading, and we know its cross-sectional area, we know its elastic modulus, we know the internal load, okay, we can calculate what the displacement, what the deformation, what the extension or contraction of that bar might be. And this was kind of this was the example that I gave at the beginning of last time. So imagine you have a rod, it has a force P acting externally on it, okay? That external P turns out to be the same as the internal P, okay? And I didn't distinguish the difference between the two very well. Okay? And today we're going to distinguish the difference between them more carefully. Okay? So here's the internal P, and then you integrate on the internal force, like you see here, and this is the expression that you get, which we're familiar with, right? PL over EA. Okay, complete. So I just want us to focus today in terms of, on the internal force P, okay, in the axial member. So here we go. Let's say, and this is the example we had last time, but I just said there's a P, and I wasn't very clear on whether that P was a load or was the internal force. Okay, and so we're going to look at it both ways. If it were to be the external force acting on the system, or an internal force along the axial member of the bar. Along the bar. So this P, and this is from last time as well, has a function m times x. So at x equals 0, P is equal to 0, and at x equals L, P is equal to ml. Okay? And m has units of force per length. Now we're going to say it's an internal force this time. And the question is, what is resulting displacement? So this is what we had written last time. Okay? But I've added an R1 on one side and an R2 on the other side. Okay? We're going to be a little bit more careful here. And this, we're going to say, even though, so this is the thing. Often, and this is a little bit different. Often, you would not see an internal force written like this. What you would actually see is the load written like this, okay? And you remember this from statics. And if it were a load written like this, it would not have units of force, okay? Distributed like this. What it would be is a distributed load with units that are essentially force per length, which is the multiplier that we're using here. Okay? So this is a little bit of I apologize. I did a kind of a poor job of setting up this problem. Okay? But I think as I went through it, I think it does shed some interesting insights into how we should go about preserving equilibrium when we do these problems. Okay? So we're saying it's internal. So if it's internal, if it in fact is internal, you don't really have to think at all, okay? You just go ahead, we have this nice constitutive equation, all right? This one holds, this is internal force, and we do the integration, and we're done, and that's exactly what we put on the slide last time. So in a sense, we were saying, hey, it's an internal force, just do the integration and you're done. But let's take a closer look, okay, as I zoom out, all right, at what is actually happening inside when we look at equilibrium. So what you have here are the three categories. Now, often we write equilibrium, then we write out geometry, then we write out constitutive equations, all right? But this time, it's kind of like when you're solving, you don't have to do it this way. You don't have to, all right? But this is Crandall, Dahl, and Lardner's kind of layout, right? And, it might waste a little bit of paper, but if you have the three columns and you keep yourself organized, it's probably worth it. Okay? So, and digitally, oops, sorry. Oh, I moved wrong. Digitally, I have the advantage of being able to write things and then move them around. Okay. So in terms of geometry, we're going to define x from the left side with x equals 0. All right, so that's what you have. That's what we have here. So that's not a big deal. Geometry is not the focus of this problem. Equilibrium is. So let's look at what's happening close to the left side. If I have this reaction force, right, which we had up here, on the left side, and I'm just like, hey, I'm just gonna like take a little sliver. Oh, you can't. Online, you wouldn't be able to see that. Sorry. And if I take a little bit of, sliver like right around here, all right, what's happening internally? Well, what's happening internally is what's been specified. Okay, P of x has been specified as the internal force. Okay, so we don't really have a choice. So when we come over here and we take a cut, and we look at this, right, really close to the left side, what is the internal force? Well, it's equal to mx, right? So x equals 0. That just means that the p, okay, is going to be equal to 0. So if that's the case, then if I'm trying to preserve equilibrium, that means that R1 also has to be equal to 0. Okay. Right? Because I'm saying there's no other external force, right? This is foreshadowing. There's no other external force acting on the system. Okay? And so if I'm preserving equilibrium, that's what's happening. Okay? If there is, if I go to some x greater than 0, all right, then what does R1 have to be equal to? Well, R1 has to now be equal to this guy, P of x, again, and P of x is greater than 0. That's equal to mx, and that's also greater than 0. But wait a second. You said there's no external force acting on this system. That means that R1 still has to be equal to Px, but R1 just changed. Okay? R1 just changed. And for statics, that's not good. Okay? Because that was the external force, let's say on a wall or on the left side. Okay? So what must be happening for us to preserve equilibrium? All right? What's happening here? There has to be an external force acting on this system. Okay? There has to be some type of external force in order to keep this system in equilibrium. All right? So this is strange, right? Because we said this is the internal load. We didn't draw the external load on the system. Okay? But there has to be something in order for equilibrium to be preserved. Okay? So, whoops. Okay? So, the question is, can R1 change? No. So what is happening? All right? It's not a comic book, but you get the idea. Oh, it's even worse. Okay. All right, maybe I won't do this again. All right. So, but maybe I will. We'll see. So there has to be an external load. And let's just call it some Fe, all right? External force, right? So here we go. It doesn't really matter where we put it. I mean, it kind of, intuitively you think, oh, well, maybe it should be somewhat distributed or something. Okay, right, maybe, right? Which is kind of what you would normally see in these problems. So there's an external force, let's call it Fe, and then when we do equilibrium here, we can say that these guys, okay, P of x and Fe could be equal to 0 if we're specifying now that R1 is equal to 0. So these two actually compensate, or they knock each other out. Okay, so that's pretty much the point here, all right? And this external force has to be equal to this internal force, okay, for this to be in equilibrium. Assuming that we say R1 is equal to 0. Like, yeah, I mean, you could have another, so it gets kind of complicated, right? You could have another force here, right? Like, kind of like an offset force if you're pushing or pulling on the right side, that you then have to do that on the left side to make things balance out. But if we say that R1 is equal to 0, then we have this external force acting on it, and it's equal to the internal force. So another thing we should also know is that the delta is greater than 0. Okay, and this is at least the way we've looked at this. That the internal force, it's moving this way. When I do a cut, since I've called it an internal force and it's coming out of the face of the cut, right? It's coming out of that exposed face. That means that by definition this is tension. And so that this bar is going to elongate, right? And so the internal stress has got to be greater than 0, and the bar is in tension. Any questions on it? So trying to take a poorly posed problem and get some further insights into why it's important to make sure we use this constitutive equation that's been derived for us with the internal force. Okay, so let's go another step. Let's say that we're going to use P of x as an effective external force. So now we say it's an external force. Well, that's just a conundrum in terms of the constitutive equation, because I shouldn't use the px, right? Because now it's an external force, not internal. So maybe I'll use something called maybe I'll use something else called Fi, all right, internal. So what's also kind of weird if you do it this way is that this P of x has units of force, which I said a minute ago is unconventional. It's not how you would think about this. And it's also hard to intuit what that looks like. Essentially it's like you have a bunch of maybe cables attached really close to each other along that thing, and you're applying individual forces at each of them, okay? That would be like one way to think of this being loaded. But that's kind of not, again, normally we're thinking of a distributed force. So first, we should probably perform external equilibrium, okay? And even though we have the equilibrium, geometry, constitutive equation columns, if we go back and we look at what we've discussed before, when you do equilibrium, you're supposed to do equilibrium externally before you go internal, right? So, and sometimes, like you see, we take a shortcut, right? But let's not take the shortcut this time. Let's look at what's happening. So external equilibrium means that I have some P of L, essentially, all right? So I'm calling it P of L. That's going to be equal to this reaction force on the right. That has units of force. I can't really integrate it, all right? So if I'm right at the right, okay, it's going to have P of L. So if we keep things simple, right, saying R1 is equal to 0, and now we say that R2 is equal to P of L, that means that R2 is equal to PL. And that kind of makes sense, that, well, it means we have to have these counteracting each other. Now, what if we start taking some slices? Let's take a slice and expose the left side. If we do that, when we do internal equilibrium now, we can say, okay, here, what we're doing, and I guess what we're saying is that, as for external equilibrium, essentially what we're saying is treating this x as the length. Okay, what it is, right? But that's like the whole force acting on the system. But if I take a slice here, okay, I want to know what the force is acting on the system, okay, externally. So I'm going to do something a little bit unconventional as well and say still defined from the left, right? And wherever I am, P of x, all right, so where I am at x, if I want the force, the external force acting on the system, on the bar, I'm going to say that it's just mx, right? So whatever distance. So as we go closer and closer, as we go further to the right, essentially, and we get all the bar in there, then it will be ml. Well, we said that R2 was ml a second ago, right? That was right here. R2 is ml. So that means that P of x is going to be less than this R2, which means now we need some type of internal force, okay, to be present to counteract, to make this be in equilibrium. We need a non-zero internal force. Okay, so that's what we've drawn here. So this internal force, draw it against R2 and with P. So these guys added together minus this one is going to be equal to 0. So now we have an expression for the internal force. The internal force can be written as this R2 essentially minus the P. Okay, and that's what m times L minus x is. So now we can use the constitutive equation with this form, okay, this Fi, and integrate. Now, it's a little bit strange, okay, to have this force P defined as it is. But the way we've defined things and the way we've drawn our internal force, we see that the internal force is going into the member. So since the internal force is going into the member, that means that this bar is going to be under compression. And if it's under compression, that means that we're going to be having a negative extension. So what I did here is I just said, okay, insert this negative sign right here, and then do the integration out so that it comes out to have a negative displacement. Any questions on this? So it's important that we figure out what the internal force is when we're doing these axial loading problems before we go ahead and apply the constitutive equation. Okay? And even though I got a right answer when I did it last time, okay, that didn't mean that the methodology that I was using was clear. Okay? Because if I had said that was an external force acting on the system, then I would have gone the wrong result. And if you see, in this case, right, they're inverses of each other, right? So this is saying we're in extension. This is saying that it's in compression. Okay. Yes. Go. All right. Okay. Yeah. So in the end, right, this is not. You can't do this. All right. That's just the point there. You can't do this. Okay. So this one this was a case where I got the right answer, all right, but I didn't do a very good job of explaining, okay, what was going on. We have a bar. It's hanging maybe from a ceiling. It has cross-sectional area A, has density rho, elastic modulus E, and we have gravity acting on its length. And so this is revisiting what we discussed last time in Column 3. And so this is the whole layout. Rho, E, A, okay, here's the displacement at the end. Okay, so this is partially done. Here we have our three columns: equilibrium, geometry, and constitutive equations. Okay. We'll just go ahead and put everything out there. Okay. So let's first look at equilibrium. With equilibrium, it's probably a good idea, again, to do external equilibrium. So what does that mean? That means that this bar, forget about the distributed gravity for a second. Just think, it's a bar. It has some mass, and gravity is acting on it. So the entire bar has to be held up by some force, R. So if I do external equilibrium, we have mg minus r is equal to 0. R is equal to mg. All right, and so this is maybe that equation I said I didn't explicitly give. Okay, that rho g times the volume is equal to force or weight. Okay, so now it's here. Does everyone see that externally, right? Rho times volume, right, is mass, times g is going to be the force. So now, why don't we take a look at internal equilibrium? So this time, we're still defining x to be from the top, all right? Now we have this external force, R, at the top, when we take the slice, and we have this distributed force, little f, okay, that is acting downward. And of course, maybe not of course, but if we want to figure out displacement, right, at the end here, we probably want to use our constitutive equation, right? Essentially, the integral of px over a e dx. So we want to use this, which means, once again, we need an internal force. Not the external one, but the internal one. So I'm going to we draw it out. We draw the internal force there. And we want to satisfy equilibrium. So a few notes here. So F here is this distributed force, and yes, it's due to gravity. Okay? And if I want to go from a distributed force to a force, okay, so I often can do some type of integration. Now, you can be careful here, right? In this case, little f is a constant. So lowercase f is a constant. It's very possible, as you saw on the homework, right? So maybe you can go back and take a look at the homework, right? Because homework was a little bit of plug and chug this time around, right? And as have been others as well. Okay, so you probably weren't looking at the free body diagram very carefully. You're like, oh, I just gotta get the numbers to work, okay? But if you look at the free body diagram, okay, you'll see something kind of similar, except the little f, okay, is not a constant, right? Because you had centrifugal load. So the little f is a constant, and I need to integrate it up to get f, right? If f is not a constant, like let's say it's a function of x, like let's say it's like, I don't know, mx or something, right? And then you have to integrate that up, right? Then that means that the m actually has units of newtons per meter squared instead of newtons per meter, right? Or if it's, mx squared, then that m has units of, newtons per meter cubed or something like that, okay? And you have to integrate up. Okay? But ultimately, you need to get a summed external force, F, acting on the bar, to then do the equilibrium with your internal force, P, and whatever other kind of bulk external forces you've calculated previously that are acting externally on the system or on the constraint or as constraints. Okay? So here, this one is maybe a little less intuitive, all right? But you have rho GA, all right? So this ends up being, this is probably intuitive here. This may be a little bit, rho GA may be a little bit intuitive, but a little less intuitive. But the result is rho GAX. So in other words, what we're saying is the external force, the big F here, is equal to the entire mass times gravity of that upper section. Okay? So like, if I wanted to, I didn't draw here, but let's say if I want a big F, right? I would put it, I might just put it in the middle, smack in the middle on its center of mass, and say that big F is equal to the integral of this little f dx. And so when we do the balance out, all right, we have P and big F and little f, but P and big F acting in the same direction, but R is acting in the negative direction. And so we get this equilibrium. And once again, we can solve for the internal force P, okay? And we get the following. Using R, which we calculated up here, minus this new term, the big F, okay, we get this expression for the internal force, P. So last time when I did this, I was not careful, okay? It turns out the answer came out right, okay? But that's not the metric we want to use. If you don't want to think about the big R, there's an alternative. The alternative is to start from the bottom, okay? Define your x as going up from the bottom, okay? And then when you take your slice and you expose the top, there's zero force on this side. Okay? There's zero force on that side. So then we consider the external force and balance with a P going up, right? So that would be P minus F, where big F is equal to the integral of this minus little f dx. Okay. So anyway, when you stick, but the easy part is once you figure out P, you stick it into the constitutive equations, and then you're able to do the math. I think people will say, and actually people have said, when you see the math, this is very simple, okay? And it's kind of a criticism of this class, or me. See the math, it's very simple, yes. But it's the equilibrium, if we go deeper, right? If the equilibrium is usually the hard part, okay? But the ironic thing is that we've taken, or we had a whole class on it, okay? On the equilibrium part. Any questions? Or thoughts? Or comments? Or jokes? We're quiet today. Okay. Linear coefficient of thermal expansion. This slide is copied exactly from what we had last time, all right? And what we said is, if you have a given length, you multiply it by, or if you're trying to figure out the change in length, okay, then we're going to have this alpha delta TL. And another option would be to have an alpha V, but alpha V, okay, that's a volumetric coefficient of thermal expansion, right? So alpha L is equal to alpha V over 3. And we discussed last time, if it's a free end, you have zero stress, but you do have strain. Okay? This thing has expanded if it's heated up or contracted if it's been cooled. And then we did a quick example at the end showing how we could figure out, using the method of superposition, how to push back on the surface or on the end, on the free end, to compensate from expansion, to pretend, or not to pretend, okay. So we pretend that the two walls aren't there, or one wall is not there, right? And then we apply force to push it back to satisfy that constraint of having a wall. And then we said, oh, well, the thermal strain is 0 because it couldn't go anywhere, but it wanted to. And it wanted to expand, but it wasn't allowed to. It was constrained. And to compensate for that, there was stress, or there was applied force divided by area. Okay, and so this is in compression, right? And I think that's kind of intuitive, right? If I have a bar and I heat it up, right, then it's gonna push on the walls maybe that it's being constrained by, and that means it's going to be compression. So let's do another example here. Okay, let's say we have a bar constrained between two walls with cross-sectional area A, two sections of length L1 and L2, elastic moduli E1 and E2, and linear coefficients of thermal expansion alpha 1 and alpha 2. If there's a change in temperature delta T, what are the axial strains in both sections? So, yeah, technically, I could give just the words here, and hopefully that might be enough to conjure the image. But here's the image, all right, or a really rough image. Here's section 1, here's section 2, E1, L1, A, and I guess I should also say that it has, there's also an alpha 1, right? And there's also an alpha 2. Okay. So, what I would like to do here, okay, is have a mouse. Where did the mouse go? Okay. Oops. Oh, I guess the mouse disappears when you use the pen. All right. So, let's use the method of superposition. All right. Let's say we remove one of the walls, and then we're going to let this thing expand, and we're then going to apply a restoring force. Okay. So, thinking about it geometrically, okay, so we have our three categories: equilibrium, geometry, and constitutive equations. All right. So geometrically, what's going to happen is we're going to have some delta 1, right, from this region, some delta 2, okay, from this region, right, delta 2, all right, and then when you add them both together, you get a big delta, your overall delta. So, the overall delta is going to be delta 1 plus delta 2. Now, we can calculate that out. So, it depends on which order you want to do things, right? But we could write out some constitutive equations, okay? And, the constitutive equation right here that would be relevant would be that the delta is equal to alpha delta TL. Okay? And so if it's unconstrained, what you're looking at is this right here. Alpha 1 delta T L1 plus alpha 2 delta T L2. Okay? So this is the unconstrained length that we have. Now we're going to think about what happens. Let's go to equilibrium now. When we apply that force again, right? So if it's unconstrained, there were 0 forces, okay? 0 stress in the whole bar. But if we say, no, I'm not going to let you expand. I'm going to apply a force. That's fine, okay? I'm applying a force. You remember on one of the homeworks we said, like, if we had a force here in the middle, right, and we're looking at that relationship between its F and its delta, it's like putting these two things in parallel. Well, that's not what's happening here. There's no force being applied in the middle. Okay, there's an action-reaction pair between the two, but I'm not adding an extra force there. So since there's no extra force there, this system is like two springs in series with each other. And springs in series, right, or bars, right, this is like saying, hey, if I take a cut in the bar and I have a force on the left side, right, then there's no other loads, right? We just did this whole thing with axial loading, and we said, oh, we had to add an external load for equilibrium to happen. But if there's no external load, then we're just going to have the internal force equal to the external force acting on the bar. So here, if I compress on this side, I have an internal force, okay, which is equal to this. But these are springs in series, and these are springs in series, so also the force on the left side is going to be the same as the force on the right side. Or another way to look at it is there's no internal force here, so they have to be the same, right? When I do my external equilibrium. Again, it might have been a good idea to write external equilibrium and do this. Okay, so these forces have to be the same. I've calculated out an unconstrained system. Wouldn't it be nice to know what the spring constant is of this entire system? Right? Well, of course it'd be nice. And I could then go to a constitutive equation and say, okay, F is equal to the K effective times delta. What is K effective for two springs in series? Well, one form is K1, K2 over K1 plus K2. So now what we can do, all right, is we say, look, there's this constraining force, and it's the same on both sides, it's the same in both springs, and the same in both bars. If I know what the spring constant of the entire system is, then we can figure out what the displacement, well, then we can figure out what these forces, what this F1 and F2 are. So it says, I know, I've already calculated how much I had to push the whole system back, right? Because that's how much it went when it was unconstrained. So now if I have a K, an effective K, right, I can figure out what the force is going to be to push it back, and that force is going to be the same in both bars. Okay, so now delta is equal to this quantity right here. This is the effective spring constant. We know from our past that K1 is equal to E1, or K, right? So here's another constitutive equation we can write down. K is equal to EA over L. So if we're interested in the K1, we can say that K1 is equal to E1A over L1, because the A's are the same. And K2 is equal to E2 over A over L2. So we have a force, and we have individual spring constants. But they're asking for strain. So how do we get strain? Well, one way to get, I guess there are a couple of different ways we could have done this. Okay, I think I chose a slightly more complicated way. What I said, all right, is that a force divided by area is equal to stress. Okay, and then epsilon is equal to sigma over E. And so epsilon is going to be equal to F over EA. So we know what the individual forces are. Okay, we need to figure out the individual forces are this big expression here, F equals K1 times this whole thing. Okay. And we have an E over A, so if I have the appropriate E1 and A1, all right, and I know what the force is, I can figure out what epsilon 1 is. So that's what you have here. So epsilon 1 is this force divided by E1A. All right, so this is that force times 1 over E1A. And then epsilon 2 is 1 over E2A times that whole thing. Or another way of writing that is cancel the E1s out and put an E2 in the denominator. And it's just like this. Any questions on this? Comments? So these types of problems, these axial loading ones and these thermal strain problems were kind of the one of the main or the foci, I guess, of many of the exam problems. You know, plus some material property stuff for exam 1. So I think that that this should equip us pretty well on this portion, and then we cover torsion, and then that should be pretty much the bulk of the exam 1. Right, so let's change it up a little bit. Hopefully you'll find this somewhat interesting. If you are an engineer, do you think you're going to use all these equations when you get in the real world? Why not? Yeah, of course, it depends. If you're a design engineer, okay, then you are going to be walking around the world like, oh, there are cables hanging there. I can figure out what their stress is. You know, if I have their elastic modulus, I can figure out what the strain is. And it's like a lot of back of the envelope calculations. All right. That's not all. I mean, that's one version of a design engineer. There are other types of design engineers where the structures are so complex that there's no way you can come up with these simple expressions. Like these expressions, we're solving like simple cases. You ask yourself, why are we spending so much time on the simple cases? Well, there are a couple of reasons. One is these are fundamental structures that we encounter, like cables, every day. And so it's nice to have some idea of scaling laws, relationships, and numbers. And two, we have to understand, or we get to understand, and we'll do this a little bit later, how the stresses in simple structures relate to stresses in complex, stresses and strains and simple structures relate to stresses and strains in more complex structures. Okay? So we test our materials. We've said this before, right? We test our materials in simple configurations. But then we want to see how these materials will work in more complex situations. One way to figure out what's going on in a more complex situation is to use numerical methods or to use simulations. And the one that you have maybe have a little bit of, actually, has anyone used finite element analysis for maybe an internship or something, right? Okay, what were you doing?
Oh, well, we just learned it in CAD.
Oh, okay, you did it in CAD, great, yeah, so you did it in CAD, right? Okay, so we're now going to show you how to use some off-the-shelf or open source software. So say you're working at a startup, okay? And you can't spend all this money on SolidWorks, I'm sorry, on some software, all right? Okay? And it's been a long time coming, but I think there are now some somewhat user-friendly, okay, open source programs. So we're going to do this. We're going to use something called Prepo Max, which uses a finite element solver called Calculix. Okay? And to do our CAD, we're going to use something called FreeCAD. Has anyone used any of these before? A little bit? Okay, well, there we go. And just some acknowledgments to these people, and also our TA and an MS student, Shivam. They should be posting a video pretty soon that we'll link everyone to on YouTube. And I think this is the video that they looked at. I'm not sure which one they looked at. but there are a number. And this guy, Matej, he has a YouTube channel as well. Okay? But this PrePo-Max, I don't think it's been I don't think many people know about it yet, but I've been very impressed. I've been very impressed with little I've used it, because like you, we use a very expensive multi-physics piece of software, okay, and that's very nice for our research and things. But we've also been trying to move into more of the open source solutions. So let's do a very simple example. We'll see if I can get it right. All right, you can laugh at me if I get it wrong. All right, but what we're going to do is have a bar, and we're going to put an axial force F. It has cross section AB, has elastic modulus E, has a I meant to say it can have some density. That's fine. I'm not going to take its density away, but we're not going to use it. It has a Poisson ratio nu. Okay. We could use it. Actually, we could use it because you can do gravity loading. But today we're just going to try to do it. Now, so sometimes with finite element, it doesn't like it if you put a big point force load on it. Okay. So sometimes you need to distribute the force. But we know how to distribute the force. We can distribute it as a pressure. It's just force divided by this cross-sectional area. Okay? And that is going to be the stress along this bar, right? We agree, right? Sigma, if this is x, sigma x is just going to be this force divided by its cross-sectional area. And I thought, do people do this? Have you guys found this yet? If you're struggling with your units, guess what? Google's got your back. All right, just put 1,000 newtons divided by 1 centimeter by 1 centimeter in whatever unit you want. Megapascals. Boom. It does it for you. Okay. I'm not saying we're going to ditch Colab, all right? But, all right, this can help if you're struggling with the units. I do this. I don't usually use the unit feature of Google, all right? But I do my math all the time in the web browser. Okay, I just punch it in, right? And then boom, it gives you an answer. Okay, and Google. Another one that I use more actually didn't do the unit conversion very nicely for me, so I was a little disappointed. Okay, but Google does. I didn't try another big one, but maybe once the other big one, once their artificial intelligence is in, it'll probably be able to do the whole problem for you, right? We'll see. Has anyone used ChatGPT? Yeah. If you plug in a physics problem like this, what happens? Anyone done that? Probably says it's poorly written or something. Okay, so what are the normal strains in the bar? Well, we can use our material properties and constituent relationships, right? If we have an epsilon x, then we think sigma is equal to, sigma is equal to E epsilon, right? And so that's straightforward. But remember that if there were stresses being imposed or present in the cross-sectional directions, right, like coming out of the board or coming up and down, right, that would have an effect as well. There are none. Sigma y and sigma z are 0. Okay, so we just have our sigma x over E, right? So then we can calculate out what the strain should be. And epsilon y, though, if we want that one, there is no sigma y, okay, but there is a sigma x, okay, and so through the Poisson ratio, we do get some strain, and it's in contraction, as is this one. Okay, sorry, I just forgot the negative, okay, as I forgot it here, too, but it's right there. Okay, so, right, microstrain is just another way of saying times 10 to the minus 6. All right, so I could have said 50 microstrain. In fact, I did say 50 microstrain when I first wrote it out, but I figured to first just write 50 times 10 to the minus 6. Okay, so let's have some fun. Let's see if we can do this. All right, and you guys had to help me remember the dimensions and the numbers. 5 centimeters, 1 centimeter, 1 centimeter, 1,000 newtons, 200 gigapascals, and 0.3. Okay. So first, and you're going to get to do this on your homework, okay? So if you don't want to use FreeCAD, you don't have to use FreeCAD, right? You could use another program, all right, to do the geometry. I'll show you though that it's very important to be very careful in one particular step when you bring it into Prepo Max. Prepo Max, it turns out, only works on a Windows machine. Okay? Sorry. But I'll show you that if you go to the EIT, I tested it yesterday. If you go to the EIT or DSV lab, you can download Prepo Max and you don't have to install it on Windows. You just run the executable. Okay? And then you're up in it. All right? So let's go ahead. We're going to create a new part. And here we're going to use, there's a part design. Part design in FreeCAD is more like your extrusion type software, all right? More like some of what you remember or you know with your parametric modeling softwares, okay? But this actually can be really simple. So I don't even have to define a plane. I just put a box there, and we said its length, we want it to be 50 millimeters, okay, or 5 centimeters, right? And then 10 or 1 centimeter. Whoops, I accidentally changed it. 1 centimeter by 1 centimeter, right? Just like that. So that's pretty much it. We just created our beam, right? I don't think you can do it much faster in any of those other packages. All right, that was really fast. Geometry, very simple. So I'm going to do a save just so, and you can see I was working on this, but we'll do it under my session files. Okay, so we'll just call this bar. And we'll say 50 millimeters by 10 millimeters by 10 millimeters. Okay. Now that's saving it in its native format. What we really need to do is we need to export it, and Prepo Max takes different formats, but and so you can use like step, but we're just going to use STL. Okay. That's what, if you've done any 3D printing, you're familiar with it. Okay, so now if I did that right, we're done with FreeCAD. So now with Prepo Max, okay. Oh, that's not the right folder. Okay, so see what happened? All right, what I did is I downloaded a zip file, okay? And I don't have it there anymore. And you can go to their website and you can see, but I downloaded, just like you can download FreeCAD as well. FreeCAD doesn't take that long to install either, compared to some of the commercial softwares out there. So here's Prepo Max. This is the file that's been extracted. And so what you do is you double click on the executable. Okay, so it's not even installed on my computer. And then it comes up. All right, so here we are. Here's the interface. It's pretty clean. So we're going to do File, and you do New, and then we're going to put in our units. Now, this is going to be a point of pain, all right, in a second. But we're going to go ahead and select meters, kilograms, seconds, Celsius. And I am sorry, you guys can't really see a lot of this, can you? This is one case where it's probably easier if you're online. I don't know how to make these things much bigger. All right, so now this is my space. It has these units here, and let's go ahead and import the thing I just created. So I had under sessions here. This is what we just created. STL. Okay, it brings it in. Does anyone notice anything that's weird? Keeping in mind that we just said that our bar was supposed to be 5 centimeters long. Yes.
The unit on the bottom.
Yeah. Look at the scale bar. This is 30 meters. All right. So this has become 50 meters. Okay. In length. So we need to get it to 50 millimeters. So what you do, and so this is also, I tried it with SolidWorks. Also an issue with SolidWorks, okay? It's okay. I mean, if you've done stuff with STLs, you know that the scaling can be wonky, all right? So you just gotta keep track of things. So we go over here to geometry, and we're going to, we go to the part geometry, we go to transform, and then we can go to scale. So what's our appropriate? It's just like, here we go again, right? We have to know our units. And it's frustrating for me too, trust me. I get frustrated by it too. I'm like, why is this not working? Right, so what we're doing is we're scaling in the x, y, z directions by the same amount, 1 over 1,000. So 0.001, okay? Apply, close, and it's gone, right? But, you know, for open source, this is pretty good. So now I can zoom to fit. And what do we see? We're now pretty good, okay? We're pretty good, okay? And, you know, it's you know, I have a mouse, so you probably want a mouse when you do this, but this is now the system. All right, so what are we going to do next? Well, next we're going to use a mesh, and we're just going to use the default, so you don't even have to come in here if you don't want to. I'm impressed. It's not it doesn't give you a super fine mesh, but it seems to give an adequate mesh for these simple geometries. Okay, and you can change the maximum element size, the minimum element size. Okay, don't worry about this for now. Okay, hit OK. And and then I had to create. That actually did absolutely zilch. All right, so I did OK. I just looked at them, and now we're going to create the mesh. Okay? So it meshes this bar pretty quickly. All right, so let's take a look. It populated our menu here on the left. Let's go ahead and let's create a material. I'm right-clicking, by the way. Okay, and we're going to create an elastic one like this, and we're going to call it steel for kicks. You don't really have to do that, of course. Okay, and then look. If I'm not mistaken, it allows you to put in 200 gigapascals, and then it calculates it, puts all the zeros, and the Poisson ratio 0.3. That's it. Okay. That's in. Now, what we do next, all right, is we create kind of the type of problem we're trying to solve. So there are like frequency-dependent ones, there are kind of more complex ones, but we are just doing, and you can see, I haven't done this yet, but I've seen some examples like, oh, it'd be fun to do like a couple of temperature displacement. We can do that, right? Prescribe some alphas. All right, so here we're just going to do static step and OK. All right, and now it gave us some extra things. So we're going to look at the boundary conditions. We're going to create. What are we going to do? Let's say we fix this left end. All right. So now it's. Oh, I know I skipped a step. We're going to select the surface. All right, like this. Okay, like that, and it's good. And it shows its little thing. You do have to define a section for it to solve on, and in this case, it's just a solid section, okay? And so what actually happens is you select the whole thing, okay? And then, okay, sorry. I should have done that earlier, but now it's done. All right, so I've got this fixed end over here, and on this end, I want a force, right? Or an effective force, or pressure coming out. So what we do is we come over here and we say, oh, loads. We create a load. And you can do a concentrated force, but if you do concentrated force, what I found, and I'm sure they knew this is on purpose, it actually puts that force on every single node. Okay? So if we're doing 1,000 newtons, it's going to put that force on all these nodes on this face. And that's not really what we want, okay? If we knew the number of nodes, we could scale appropriately, that'd probably be just fine. But instead, what we're going to do is we're going to use an uniform pressure. And we're going to select this face, like that, okay? And then it says pressure. Now, pressure, right? We've done pressure now in the class, right? We know that it's acting toward the inside of the object, okay? So if I do 10 megapascals, which is what we calculated a second ago. Okay, and we hit OK. I don't know if you can see that, but it has drawn it internally. Okay, it's drawn it going in, and we could solve that problem, but let's not. Okay, let's just go ahead and change it to be minus. Okay, so now it's coming out. Once we've done this, I think we're ready to solve. I can't, probably forgetting something, but I don't know. So you go over here to analysis, and you say run. Yes, we're going to, it's fine, overwrite the current one. It did it really fast, 0.6 seconds, and we look at the results. Okay? So, what do we see here? We first see that it can give us displacement, all right? And you see there's an X, Y, and Z direction here. This is exaggerated, okay? You see that the factor, the deformation scale factor is 1200. It didn't really go from here to here, okay? That's been multiplied by 1200. And the displacement is about 2.5 microns, so it's not that much. Now, I didn't calculate displacement, but I could, right? I could have, or I could say it's going to be, like if we go back here, all right, I know that it's supposed to be 50, okay, microstrain, all right, 50 microstrain, and it's times the length, right, is 0.05 centimeters. Okay? So if we multiply these two against each other, so that's 0.05, okay, times 50, all right, that cranks us up to 200, or 5 times 50 would be 250. That, and then we have to move over a little bit, 2 zeros. Okay, so that actually takes us to about 2.5 microns. Okay, I did that calculation pretty fast, but 5 centimeters times 50 microstrain should be 2.5 microns. And what do we get? Look at that. It's 2.486 times 10 to the minus 6. That's pretty awesome. Okay. The real questions that they wanted us to answer, or I said, is let's look at strain. So for strain, okay, so another, like a dummy check, all right, maybe it's not that dummy, all right, is let's look at the stress first. We said that the stress that we're applying is 10 megapascals, okay? So 10 megapascals is 1 times 10 to the 7 pascals. And you're like, wait, the max is like really big. It's like, it's 17 or something, right? Okay, that max, look, this max is up here. It's like in this region, or it's over here. It's at this corner. Okay. What's happening, right? This has Poisson ratio. Okay, so it's, and then there's these discontinuities. It's constrained. It's fixed on the left end. It's not allowed to move, right? Whereas over here, once we're sufficiently far away, and this is called the Saint Venant principle, once you're sufficiently far away, you can approximate things nicely, shall we say. That's a really bad way to say it, but you can approximate as just, force divided by area, essentially. So this stress, now what is S11? S11 is sigma 11, all right, or sigma 1, or in our case, sigma x. Remember that? We have that notation. So look, if I look at this kind of bluish color, I see that, oh, it's kind of looking like it's over here, all right? It's like 10, something like that. And what's cool is that, and let's just do it over here, or I don't know, we can do it wherever we want, I guess. But if I can pick, I can do a query, I can put a node there, and whammo, right there, is what did I just do? Okay. Right there, it's saying the value of that node, okay? Oh, and it's actually, I guess it's telling me at different nodes, if I so desire. It's 10 to the 7, or it's 1 to the 7, right? 1 times 10 to the 7, sorry, 10 to the 7. And over here, 1 times 10 to the 7 as well, okay? So, yes, the FEA is working. All right, let's go to E11. Whoops, let's close this first, okay? E11, right, would be epsilon 1. Okay, that would be epsilon x. Right? What did we calculate? We said just a couple seconds ago. We said a few seconds ago, we said that it was 50 microstrain. Look, 5 times 10 to the minus 5. Yeah, all right. Now, let's see, what should sigma y be? We said sigma y should be minus 15 microstrain. Okay, I don't know if this is going to work. I haven't actually done this, so this is dramatic for me as well. Yes! Yes! Minus 1.5 times 10 to the minus 5. Minus 5. Okay, epsilon 3. Yes! Okay, I'm so excited. This example actually worked. Okay, so what we're going to do for your assignment, it's going to be super exciting. You're going to get a set of dimensions. You're going to build a block in FreeCAD or in your SolidWorks or whatever you want, and then you're going to do exactly the same thing. You're going to calculate out those values, and then I want you to take a screenshot showing that you can query and get the same things. Okay, and that's what you're going to upload to Canvas. Okay. So this is recorded, should be no problem. Okay. Any questions on this? What do you think is easier? Is it easier to do analytically, or is it easier to use the software? Well, let's put it this way. If you have 2 watches, do you know what time it is? No, right? You don't know which one's right. So when you do your simulations, okay, you should first start with the baby case like this, okay? And make sure that you're setting things up, you get analytical responses, or your analytical response matches your simulated response. After you've done that, you can go ahead and you can try to do things. Oh, there's one other really cool thing I want to show you here. So let's just say that you have to change the geometry for some reason. Just hypothetically, all right? Just hypothetically. Look at this. If you click back on this geometry tab and you go over here, you can, where is it? Yeah, here it is, edit. You can regenerate using other files, okay? So watch this. Let's see if I can do it. If I have another STL file, let me see if I have another STL file. Yeah, where did I put all those? Okay, I don't know if this is gonna work. I did it before. I was like, you gotta be kidding me. This is so cool. So I put that one in, all right? So this one. Okay, so guess what? Not quite perfect. Because it wasn't the same, right? What it did is it put the fixed constraint on this side, and then it put pressure on the top, okay? Not quite the same, all right? But nonetheless, I should be able to run analysis. Okay, yeah, I see some funky results, right? So if you keep your orientation all the same in your CAD, and for some reason you might have to change the geometry, okay, because maybe it didn't work out exactly like you thought it was going to, you can actually just change the geometry in your CAD and then go to edit and then pull that in, and it runs the whole thing again for you. Okay, so that hopefully will be a time saver for some of you. All right, I'm super excited. And now there's like no time. No, I'm not. I'm not gonna. No, I'm not gonna save that one because I just did all that stuff. Okay. It's not so bad. We've got 6 minutes. You don't have an assignment, so let's go back and let's review some things about torsion. This slide was from session 2. Okay, remember that when we did bars, shafts, beams, trusses. We said, hey, we know how to do all these because we took statics, or we know statics. Okay, so remember we do external equilibrium, and then we take a slice, and we can figure out what the internal torques are in a system, like so. And it matters which direction you take the slice, and then you can apply Newton's second law to figure out what the internal torque is. And in this case, it's equal to the external torque, TA, and it's also equal to the external torque, TB. Okay. So why am I doing this? Why are we reviewing this? Because we want to now take our expanded understanding of material properties and relate them to torques that are applied. Okay, so we don't forget our equilibrium, and we're going to keep using our equilibrium. Okay, and today our goal in the next 5 minutes is to get to understanding what the shear strain is in a rod that's being twisted. That's our goal in 5 minutes. Okay, so we have. This is also from session 2. We have a shaft. Well, it could be a rod too, but a shaft that's undeformed, right? And we said when we deform it, we had these types of shapes, okay, that were nice. Like we drew the lines in the undeformed case. When we deformed it, they began to skew, like we showed here. And in this case, right, the torque is being applied in this direction. You can kind of see, this element that was over here is now somewhere over here. This element that's over here is now somewhere over here. Okay? Or actually, I should say it's along these lines. Okay, and if I look at an element, it's now skewed because this side was taken to that side. And we said there could be some shear stresses. So we're not going to talk about shear stresses. Not we're going to derive the relationship for shear stresses today. That will come on Tuesday. But let's just look at what's happening with shear. Later, this is session 4 maybe, when we talked about stress and strain. Okay, we described shear strain. And this is what happens when you have a box or some type of shape with two parallel surfaces that slide against each other, okay? Or slide. So here, what happens is if there's some type of traction vector or some type of stress applied there, what do we see? We see that the box gets skewed into that shape. And then we defined shear strain in terms of how much it displaces this direction, okay? And what the height is. Okay, so zooming in, that's what shear strain was. Okay, this is X, that's Y. Well, we just looked at this kind of overall picture. If I was a better professor, right, I have a nice sample here with lines on it, and I twist the rubber, and you'd see the things, do that shape. But I look similar, right? That looks similar. So what's going on? Okay. Here it is, and I think maybe it is better to zoom up if I can. Okay, let's start here. We have these nice grids that then get skewed when we apply torque. Which direction is the torque being applied? TZ, it's coming out, right? So it's going thunk, like that. Now, let's turn things sideways, and this is the undeformed state. Okay. We haven't applied a torque, no torque applied. That will happen over here. And let's define some parameters. We're going to say, actually, I should have mentioned this before. I like to think of these cylinders as a bunch of pizzas stacked on top of each other. All right, so you go to some pizza joint, right? We have a lot of them. And just imagine you take all the pizzas out and you put them in a big stack, all right? And now I want to look at what's going on at this pizza in the middle. So I take apart the pizzas and I can look at it, right? So here's a really bad looking pizza, all right? And here is actually a surface on the pizza. Okay, I had to cover this again. I can't keep you guys. But the point is, there is shearing I'll cover this. Man, all right, I'll cover this at the beginning of our next meeting together. All right. Thank you guys. This was fun. I hope you enjoy using Pre-Pro Max and some CAD to be able to do simulations of the problems we've been studying. See you all on Tuesday.
Have a good week.
You too.